Yeah. Hi everyone. Today we have Audrey as our speaker. He's a PhD student from Yale, and he's going to talk about his new work, TreePIR, Sublinear time and Polylog Bandwidth private information retrieval from DDH. Let's welcome him.
All right. Yeah, thank you for having me. Thank you, Elaine, for inviting me. I've had a fun day. So this TreePIR, for short, is joint work with Bhavis, my advisor at Yale. And it's exactly what it says on the slide. It's sublinear time and polylog bandwidth private information retrieval from DDH. So let's look at an overview, or if this works, let's look at an overview of the talk. So first, I'll give some introduction to PIR. For those who are unfamiliar, although I know you've had some recent talks in PIR, so I'm assuming some familiarity. Second, show some past previous approach to client-specific reprocessing PIR. And finally, hopefully, spend most of our time looking at the new technique used in TreePIR, our scheme, and its evaluation. All right, so with that, we can get started. Please stop me with any questions. It's much easier to make this interactive. Okay, so private information retrieval, I like to call it private retrieval of information because I think it disambiguates the private, which confused me in the beginning. What's private is the retrieval, the information, not necessarily. And what does it mean for the retrieval to be private? Well, private information retrieval is typically seen as a protocol between a client and the server, right? So the client starts with an index I, the server has a string DB, and the goal of the protocol is for the client to learn DB at index I and the server not to learn I. But what does it mean for the server not to learn I? Well, we define this, this is a simulation-based definition of privacy where from the server's view, you can replace the client with this algorithm sim that has no knowledge of I. And from the server's view, interacting with the client or this algorithm sim should be indistinguishable. And that's how you prove that the server is not going to learn anything. All right, so that kind of defines the main idea. PIR, what is this PIR good for? Well, we see some applications. So there's this nice work on Usenix 2016 by Gupta et al. That uses PIR for private movie streaming. There are some other nice applications in metadata hiding messaging and how to achieve censorship-resistant communication in general. PIR could be a good tool. And finally, some application on how to protect yourself from malicious clients without revealing information about the websites that you're accessing through a checklist. This is very recent work. So these are some use cases of PIR and why we think the problem is important. So I figured I'd start with a small example of some way to do PIR over a database. So we consider this 4x4 database. And let's say we want to access this index on the second row, third column. Well, one easy way to access it is we initialize this index vector of size square root of n. You encrypt it with some linear homomorphic encryption, and you multiply it by the database. And then if the client encrypts the index vector, multiplies it by the database, and the server multiplies it by the database and returns this to the client, it's easy to see that what the client gets back is the encryption of the whole second row. And then it can just index decrypt and index locally the index it's interested in. The privacy of this will follow from the privacy of the encryption scheme. And the communication is proportional to square root of n of the size of the database. So this is one way to solve PIR, but there's many things here that look off, right? So in a random access model, you can do this access with log n communication and all of one time. So why do we need pretty much square root of n communication and linear time? And it begs the question, can we do better than this? And unfortunately, this first question, can we do less than linear server time, has been shown for a long time now to be impossible for a single query. So you need to do linear server time to perform this private query over a database, at least for one query. But many of the use cases we saw use many queries, right? So in metadata hiding messaging and streaming, you're going to want to access this database many times. And so maybe we can hope to do better by amortizing our time over many queries. And the first approach that one could think of is the server can run some pre-processing on the database by itself, after which any client can come in and query the database for some index privately, right? And for a long time, there was no good way of doing this from standard assumptions. And this was my slide actually, so I crossed it out because recently there's been some nice work by, actually they presented here, I think, Ethan, Weikai, and Daniel, where they kind of, they go through this approach where the server runs the pre-processing on its own, and then serves any client. So the work is a great direction. I think there's still to be proven whether we will be able to implement this direction in a practical manner, but it's a nice future direction after a long time of pretty much since 2000, where there was no big progress on this server only pre-processing from standard assumptions. Okay, and because of this, people have come up with a second approach, which is the server and the client jointly run some pre-processing, after which this client can run many queries amortized its query time. Okay, and for the purpose of this talk, we'll focus on this. Because here we know how to do we have some implementations, and we'll look at how to improve it and optimize hopefully server time and communication. All right. So lastly, on the introduction to PIR, the last thing I want to introduce is the two-server assumption, where the database that you're querying is replicated in two servers. And the privacy definition that we saw holds with respect to each server, but it also assumes, so this assumption is that these two servers that hold the database will not collude, so they'll not talk to each other. And this is because in many of these schemes, if they talk to each other, the privacy goes down the drain. So this is what we're going to be using. It is, however, a commonly used assumption because in practice, you can try to have two companies host two different servers, and this could work. Okay, so this kind of summarizes the introduction. Are there any questions here? Everything clear to the finish? Okay. All right, so now I kind of brought back the title to add some amends to the real title, which is even more of a mouthful. But so if you're being completely technical here, you need to add this amortized two server and the pre-processing the client specific case. Okay. And so now let's look at kind of how these client specific pre-processing PIR schemes work. All right. So in general, there's one framework, which is in an offline phase, before the client decides to do any query, it interacts with the server in the following manner. It picks square root of n sets of square root of n elements sampled uniformly at random, without replacement. And you send these sets to, so these sets have elements which are indices from 0 to n-1. You send these sets to the server will compute the parity of these sets, where we define the parity as the database at the index, the XOR of all the indices given by the set. So for every element of the set, we take DBS and we save it, we XOR DBS and we save it to this parity. And the server returns all these parities, so there will be square root of n of them, returns all of these to the client. And this is so that when the client wants to run a query, I guess there are some additional considerations here. So for each set, we have that each index is in the set with probability 1 over square root of n. And each set is sampled independently, so they're not related to each other. Okay, so if we have these sets, one can think of a way to perform this query in a sublinear time by just when you want to access some index on the database, you find some set that you had preprocessed that has this index. You remove the index from the database, from the set, and you send it to the database. Okay, and if the database computes again the same operation that it did before, and returns the parity of this set without the element that you're interested in, the XOR of both parities will give you back the element of interest by the property of XOR. Is this so you sent one set with I guess square root of n elements, and online you sent the set with square root of n minus 1 elements. The element of difference is the element that you're interested in. So if you XOR both, you'll get exactly the element that you want. Okay. Hopefully this is clear. Okay, but of course there's some things that we're sweeping under the rug here with the happy query and I mean the problems are, so what happens if we don't find a table entry of X? How do we proceed? And also, I think more importantly, does this client query satisfy the initial definition of privacy that we saw? Which, if you think about it for a bit, it won't exactly satisfy it, because when you remove X from the set, you're guaranteeing that the server does not see X. And this means that the distribution that the server sees is dependent on X, the element that you're querying. So you cannot simulate it without this knowledge. And so we don't satisfy the privacy definition. But
so for server 0, like, do you partition or like everything to the server of the sets, or can these sets overlap? So there can be something not covered.
Right. So for reasons that are not clear here exactly, the sets overlap. So each set is sampled independently. If you were to sample, right, like the sets related to each other, then you're right, it wouldn't overlap. But the reason that we do it this way is that later we will want to replace the set. After every query, you need to replace the set.
Oh, I see.
And to support more queries. And if you have just square root of n sets that don't overlap, you cannot replace this without having to replace it with exactly the same set.
Yeah.
So if you can replace it with just another random set, it's fine. This is just some intuition, it's not formal, but this is the reason why you pick these independently, each set. Okay. Yeah, so that means that there is some probability here, which you can remove this by just preprocessing more sets. And finally, right, how do you support multiple queries? It's the other consideration that we're not going to consider here, but the main idea of all the protocols kind of revolves around these two steps, and then how to solve these are kind of specific to each paper. But the conclusion is that there will be some solution to these, which we'll not worry about it for the purpose of this talk. I just wanted to give you kind of the model that we're working. Okay, and so, well, all the reason that we started this was to see if we can get better efficiency. Does this protocol give us any better efficiency? Well, as it is right now with plain text sets, no. But it's clear that the efficiency of this protocol is kind of tied to these sets in general. So the works that we're going to look at kind of work towards improving the representation of these sets and how we can operate on them. Okay, so there's been three main previous approaches, I think. Hopefully I'm not doing anyone any injustice. So the first idea by Kogan in 2019 was to represent these sets with a pseudorandom permutation. So basically, each set is defined by a key, and the set is defined by the first square root of n elements of the permutation, as in the left-hand corner there. So the elements of your set are P1, P2, P3, Pk. So you can enumerate them fast with the key. So going back here, this step here would only take square root of n communication. And crucially here, when you need to find a set that contains X, the pseudorandom permutation supports inverting. So for each set, you can test the membership very fast in pretty much all one time. And so you don't need to enumerate every set. You can just do one operation, which is the inverse of the PRP, and you check if this inverse is less than square root of n. And if it means that some element in between 1 and square root of n mapped to this. Okay, right. So this PRP approach gives us sublinear client space and time and offline communication that is also sublinear. But the problem is there's no good way to removing sets from these PRPs, so you cannot manipulate the key in a way that you can send it on this step here. So the second line of the first bullet point, when you need to remove it, you actually need to evaluate the set, and this ends up being square root of n log n communication, which is more than the unsecured benchmark of log n. So this is one of the drawbacks, and the second drawback is that these pseudo-random permutations over small domains are not great. Their security is worse because you need to make sure that if the whole domain is evaluatable, then you run into some other issues. Okay, so that was the first attempt at this first. So this other paper checklist, it says, well, this communication is bad, so let's just represent the set with a PRF instead. And with a PRF, we have a good way of taking one element of one evaluation, removing one evaluation from the range of the PRF with these punctural PRFs, which I'll introduce later. So this approach maintains a logarithmic communication, but it pays the price that you have linear clients or client's time or space. So, and this is because the PRF doesn't have the nice property of the PRP that it's invertible. Okay. And finally, there's this other very beautiful approach by Xi et al., which achieves very nice asymptotics, but at the price of using some very heavy primitives. Right? So it leaves the question open. All these works leave the question open whether we can design a client-specific preprocessing PIR scheme that achieves good asymptotics and has fractal value. Right? I think here's a good place. I went through a lot of stuff very fast, maybe like 4 papers. Do we have any questions? Is there anything that I could clear up? Okay. All right. So if there are no questions, we'll move into the most interesting part of the talk anyway, so it's fine. And where we'll see the new techniques used in TreePIR. Here we'll try to spend more time to make sure that it's clear, look at the new scheme and how it behaves. So zooming into everything that I talked to right now, really what we want to achieve are sets that have 3 properties. So you can describe them concisely, you can test membership on them fast, and you can describe them concisely even after you remove an element. So basically you can manipulate the key to remove an element. Okay, and as we saw, so none of the previous, I guess the last previous approach does it, but none of the previous approach does it in a practical manner. Okay, so at this point, I'll also introduce this primitive that will be useful for us. It's a puncturable PRF, and basically it's the same thing as a regular pseudorandom function, except we have 2 extra algorithms, puncture and punc eval. where puncture basically manipulates the key and removes the evaluation of one element. So after you puncture at a point I, this key is no longer, you can no longer evaluate it at I. That's the intuition of it. And the privacy property that this satisfies is that if an adversary is given a punctured key and the output at the element that was punctured, or a punctured key and a random output and a random y from the range, it cannot distinguish between these two. So basically, it's again that game where it gives no information about eval k at x, this punctured key. Okay, is the puncturable PRF?
Isn't that the left-hand side you have output part? Oh, it's no more eval.
Okay, yeah. If you're trying to evaluate at the element that was punctured, it doesn't know how to evaluate, so we're just calling it pot.
Mm-hmm.
And the correctness that we want is that for the elements that you did not puncture, it evaluates the same thing as before. So basically, it's all the same except you remove one element from consideration.
So by the same value, you mean eval with key k and value x. Not value x, at point x.
Right. Yeah. So I mean, for everything that is not the point that was punctured. So if we puncture at x, and we try to evaluate the punctured key at x prime, if x equals x prime,
Then you cannot.
then you cannot. But if x does not equal x prime, then it should be the same as before.
Does the key have to be, or the punctured key have to be indistinguishable from the original key?
No, as we'll see, it has a different format than the. We'll see a sample construction here. It has a different format, and it should be indistinguishable. Yeah, that's no.
Okay.
Anything else about the punctual PRFs? Okay. All right. Okay, so given this punctual PRF, we'll try to some new approach to constructing these sets. Okay, so using this punctual PRF that maps log n over 2 bits to log n over 2 bits, we'll define our set as the concatenation between a string I that's about half the size of the domain and the evaluation of I. Okay, and what this will give us intuitively is a set that's partitioned. So for every element, so for every partition in zero, for every partition of size squared of n, you have one element that's like randomly picked within it. So that's basically how we're defining the set. We'll have a picture, hopefully. Not here, but we'll have a picture. But so for every partition squared of n, you have one random element picked within it. That's the intuition. And so what this set gives us is that you can test if an element is in the set very, very fast. So you just pick the first half of the string and you evaluate it. And if this evaluates, if the PRF evaluates to this, then this element is in the set. If the PRF doesn't evaluate to this, it's not. So this is how we define the set. So this is how it has to be. And so you can do this with one PRF evaluation. You check if an element is in the set. Whereas before with the PRFs, you took you had to enumerate the whole set. Now you can do it with one evaluation. You just check the specific chunk where X belongs to and check within it. But so we achieve a concise description. Our set is defined by the key. We achieve fast membership, but we don't achieve hiding puncturing, right? Because as we said, as the question by Justin before, so the punctured key is distinguishable from an unpunctured key, and specifically, there's no guarantee that it hides what element you punctured, just the output of it. And so we're revealing the whole first half of our index that we're interested in. pretty much. Okay, so can we hide this puncturing index? I think is the overarching question of the work. And there are some work in it. There is some work in hiding the puncture index. They're called privately punctured PRFs, but currently the known constructions are not very practical. And so the question is, can we do this hiding from symmetric key primitives? Okay, and here I brought a picture of like a sample puncturable PRF. So we define, so this is the initial PRF construction by Godrich, Goldwasser, and Macaulay. And so G is a pseudorandom number generator that duplicates so given K, it outputs a pseudorandom string of double the length. Okay, and so we take the first half of it. So to evaluate the f of 0, 0, 0, we run this pseudorandom number generator 3 times and take the first half of the output each time. And this is what's represented by the 0 here. So the 0 means the first half of the output of G. And so they showed in this paper, I think in the 80s, that this is a valid pseudorandom function. And it's a nice construction because it also implies the puncturable PRF that we're interested in. Right. So how it does this is your key. So before the key of the PRF is just K, it's the initial random string that is used to evaluate everything. But if you want to remove just evaluation of one element, let's say 0, 1, 0, you can basically just remove the whole path to it and send back and define the punctured key as the log n strings sufficient to evaluate the rest of the points. Does this make sense?
So now the key consists of 3 parts. Those 3.
Right. So right before the key was K, and now it's G00, G011, and G1K. And from these 3, you can evaluate all the other points except for this one, right? Okay. But right. So the key is actually more than this, right? You need these 3 parts for sure, and you also need the punctured index, because if you don't know what index was punctured, you don't know how to organize these.
I see.
Okay. So, and specifically, so I think the most concise description of this punctured key is an ordered array of these 3 and then the index. And given these 2 things, you can fully reconstruct the whole PRF except for the point that you're interested in. All right. And so, but what we wanted to hide in the first place was this index I, right? Because it was leaking information. So the idea here is, what if we just define our key to not have I? Okay, so instead of sending these 3 things and the index, we just send the 3 pseudorandom strings not in the path and no I. What can we do with this? So let's look at a bigger picture here. So again, we have this punctured key here, defined by these 3. All right, so as we said before, the punctured key can be expressed as the array and the index I. But what could the server do with just the array and no index? So I think this is the question here. Is there anything useful that you can do? And so what the server knows is that I is some element between 0 in its range, right? So it has to have punctured something. It's one of these, so it can guess randomly, right? And specifically here, if we just have these 3, right? So if I just send you an array G00, G011, and G1K, and you guess, oh, maybe this should be 0. Okay, this should be 0, maybe. Okay, so if you guess, but let's just rename it to 1. if you guess 1, and you try to reconstruct it from this, you'll get something. You get a tree, of course, and it looks completely wrong at first. But what you notice here is that, some of the evaluations are the same in both trees, right? So if you're guessing just something random, the first index, right? So you get that all the evaluations here will be the same for this guess and this correct tree. And if we look at more guesses, so if we guess the next index as the punctured index and reconstruct this tree again, we get something again that where half of the evaluations are correct. And if we go through this a couple times, we start to see a pattern, and specifically the point is that very little changes between each guess, or on average very little changes. So between a guess of 0 and a guess of 1 for your punctured index, the server only has to change 1 evaluation, and then for a guess of 2, it's some more evaluations, but in general it's less than changing the whole thing. Okay, and this observation kind of led us to define this new primitive that has some unexpected property. So it's similar to the puncturable PRF that we see before, but now our P eval, where before it only took the Ki and X, now it takes a guess, J. And this is the guess that will let the server reconstruct the tree a certain way, if you think about it like this. Is it clear kind of how the server goes through each iteration? Should we spend some more time? We're good? All right, and so that's in the interface, that's the main difference here. But the security definitions will be a little different because other than the security definition that we had for the punctural PRF, we have this additional privacy in puncturing, right? Where the privacy in puncturing lets us say that 2 keys punctured at different places are indistinguishable from each other. Whereas before this was not true, because it was necessary to leak this puncture index. So if we remove the index, the server has no way of knowing it. Is kind of the intuition behind it, but okay. So this is an additional privacy property that we get, and by itself it's not really useful, but the other property that we define is this efficient full evaluation, where given a punctured key, the server can guess. So in the limit, the server can evaluate the full range of the PRF for every index, for every guess of a punctured index in n log n time, whereas naively it would take n squared time to guess a puncture, build the tree, and evaluate each one. If you use a property that we saw where the keys change very little in between guesses, you can actually evaluate all of them in n log n time. And
so this partitioning structure, like if you get rid of the partitioning, then it doesn't work. Like right now you require like 1 index on every squared aspect.
right.
So if you don't impose that restriction, I mean, I guess like you could have duplicate indices, but is that really a problem?
So the reason we do this partitioning in the first place is that it's the most straightforward way that we thought of also supporting this fast membership, where you can test if something isn't a set. You're referring to the sets, right? Yeah. So then you can, for a certain X, you can just check its partition, right? Rather than checking everything. So that's where it helps us. And also it reduces the domain and range of the PRF to square root of n instead of the full n. So I think these are the two. Yeah. I haven't thought of it. It's an interesting point. Okay. All right, and so let's look at how to construct some sets from these things. Hopefully the sets will be more clear now. I think we have some pictures. Okay, so we saw this before, we're seeing it again, but now they're weak privately punctual PRFs, whereas before they were punctual PRFs, right? Again, we're doing this partition that we just talked about. So we define the set as you pick one random element within each partition of square root of n in the domain from 1 to n. Okay, and how this looks like in a small example is if you have n equals 16 and you want to create a set here in this domain, you will evaluate the first, so these strings here of size 2, log n, so log of n is 4 divided by 2 is 2, so we pick strings of size 2, so the domain and range is size 2, so the elements of our set will be exactly the input and the output of these evaluations here. So 0, 0, 0, 1, 0, 1, 0, 0, 1, 0, 0, 1, and 1, 1, 1, 1. So there's exactly one within each partition here. Just as before. So actually there's no change here for the unpunctured key. It looks the same. And then to remove an element x from the set, you puncture the first half of x, right? And wait. And so let's suppose we want to remove the element 0, 0, 0, 1. So if we puncture the key at 0, 0, from the guarantees we had before, we're hiding 0, 1, the evaluation. And from our new guarantees, we also hide 0, 0, the puncture point. And so this completely hides the element that was in the set before. Are the sets clear? Yeah. Okay. So we send the punctured key to the server. How does it enumerate it, right? So we use our property of efficient full evaluation. And the server can evaluate every guess of an index. So it evaluates basically, it computes a parity of square root of n different sets, one for each guess. And because our efficient evaluation, it does this in square root of n log n time. And out of all these parities it computes, one of these is the one we're interested in. And so if we zoom in here to, this is our protocol, but if we zoom in just to the part of the server computation, so it takes in this punctured key, and it computes all the square root of n parities by evaluating the punctured key. So for every I, so right, again, naively, this would take n time, but because of full efficient evaluation, we can do this in square root of n log n time. And so it computes these square root of n parities. And here, we still haven't solved the problem of the good communication, because right now it computes the square root of n parities and it needs to send them all back. And the last observation that we need to complete the scheme here is you can recurse here. So you have an array of size square root of n and you need one index from it. It's exactly the problem of PIR again, but over square root of n indices instead of n. And so here you run a second PIR over this smaller database, and you can retrieve it with better communication. So that's kind of the last step to achieve the polylog communication that we promised in the beginning. And you can do this from the DDH assumption. That's where it comes in. Though it doesn't come in anywhere before then. Okay. And so, well, we implemented our approach and we compared it to some previous schemes. We didn't bring communication and this does not account for the recursive step. So basically here we're having square root of n communication, and the best single server scheme that we know that is more practical today, we use Spyro. That was the best in our tests, which for non-preprocessing PIR, and it takes around 60 ms. So the number you're seeing here, you can add about 60 ms. So you can see that in this case, for a small database, checklist would still outperform PIR, our TreePIR. But if you look at bigger databases, then checklist starts losing traction because of their linear storage. And we maintain good storage, and here, where the query times are a little longer, 60 ms does not seem like so much anymore.
Wait, why checklist needs to download the whole data?
No, it doesn't need to download the whole database, but
Why is it linear?
right. Well, you can pick between linear time or linear space.
Because it's that scheme is like the space times the bandwidth. So, you know, you can either pick square root and square root and or you can pick polylog.
Oh,
There's no
They're picking polylog and linear.
there's no fast membership.
I see.
So you can either choose to check each set or you can store a hash map on the client. And this is what we considered here because this is what they did on their scheme. And it's valid in some cases where the database elements are very big and your database is not so big. But as soon as you scale up the database, it doesn't perform anymore. Right, and the DPF PIR is just a baseline non-preprocessing. Okay.
Why is the client storage the same for this?
Oh, for the previous one, this just happened to be the case because of how we picked the size of each element in the database. So if you do the math here with the 256 and 32, yeah, it'll just come out to be, yeah.
The
But
difference between the number of elements in the database and the size.
yeah, it ended up being exactly the difference, so it looks the same. But yeah. Okay, and then finally we also were thinking of this locality problem, which I discussed with Lane today, and maybe we'll have to look more into it. But basically, we can further improve our scheme by pre-processing maybe the sets one chunk of the database at a time, since our sets have this nice property that the first element of the set is always within the first chunk of the database. And we think that this will lead to further improvements. We'll have to run some more tests to see. Okay, and that was all I had. But it was a little fast, but do we have any questions? Any other questions about the scheme, the deficiencies?
So when you do the recursion, and which scheme did you implement with it?
We use Spyro. The reason for Spyro is, from what we saw, it's the best performing one for no preprocess.
Spyro, is it the one from MIT or DDH? I don't know.
It's David Wu and some year. Yeah, and the one from MIT, they preprocess, and since our database is dynamic, it doesn't work.
But the one
The new one has simple PIR, yes. So that's why we didn't. Although it looks like a good. Okay, I think that was it. Yeah. Thank you, guys. I didn't even look at the chat.
There's no.
Okay, we're perfect.
No worries.